example, say we have the universe of students in Cavendish University. But when you want to analyze students in Cavendish University, mathematically, as an approach to problem solving, you can't just bump all those students together. You understand? So you look at the universe of students, then look at the particular thing that you are trying to study about those students. Okay? So for example, it could be the faculty in which we want to find out the universe of students at Cavendish University. Then we want to find the distribution of students in different faculties. So what is going to happen? We shall have the diagram, the universe, so we represent the universe using that rectangle, okay, which you are seeing online. Then we are able to represent the different entities using those, what do you call them? Are those circles or ovals? Yeah, they could be ovals, they could be circles. So if, for example, you represent the universe, that universe could be, the rectangle could be students, and then you start looking at the different faculties, and you try to look at the relationship between those faculties using those ovals or circles. Okay? So you will go and write in that universe inside, you write A, that could be Faculty of Science and Technology. Then B could be Faculty of Business. Then C could be Faculty of Law. Okay? But the question that comes at the end, what are you trying to study? What relationships are you trying to study about these elements? Now, it could be in terms of the number of students. Okay? So you could go into A, put there the number of FST students. B, put there the number of business students. C, put there the number of students in law. On the alternative, you can use that Venn diagram to represent the number of students where the universe is just Faculty of Science and Technology. Okay? But you are trying to look at the different students in the faculty. You can just put your whatever on silent. Okay? You put the different number of students in the faculty and look at the different courses they are doing. What do you think the ovals in that rectangle will be? What will the ovals be? Yeah?
The ovals will be what they have on the common.
No. Just from what I've said. If, for example, okay, what will the rectangle be? If I'm looking at the Faculty of Science and Technology, what will be our universe? What will be our universe? Yes, students of science and technology. Remember, we are learning problem-solving skills, so don't just cram things. I'm trying to see how you can be able to get something from a complex area, and you try to find a ways of making representation. This is data representation. That's why it's not about cramming and getting, because you are going to get a certain scenario, and you need to think of how you can be able to break the thing from being bigger into smaller chunks for you to start looking at how you can solve. Okay? So with sense here, I'm trying to say that if, for example, you have been told to go and analyze students in the Faculty of Science and Technology, your universe is students of Faculty of Science and Technology. What represents those students, the universe? What type of shape? Yes, the rectangle. So that rectangle there, you can whatever, do the rectangle and then just write on the line and say FST, so that somebody knows that this universe I'm talking about is strictly about FST. If somebody starts complicating things about law there, he's completely out, because you're putting focus on Faculty of Science, and it's the universe at that time which you are discussing about. I don't know if you get my point. Then, in that Faculty of Science and Technology, you are now maybe looking at, you now start breaking down the universe. The universe is students of Faculty of Science and Technology. However, which categories of students in Faculty of Science and Technology exist? Then you go to BIT, you go to Software Engineering, you go to BIT, you go to PCS. So now, how do we represent those? That's why I was saying we have used the rectangle to represent the universe. Those other subcategories and entities, we represent them using the oval shapes. And depending on the relationship. Now, the relationships there could be either you are looking at maybe the common subjects they are doing, how many students are doing BIT, how many students are, you could start looking at what courses they offer. And you'll find the relationship, some of them, they are merged. If, for example, you talked about a class, a subject like discrete mathematics, you'll find that those who are doing discrete math, they come from BIT, others come from computer science. Okay? We'll find others where, if he's doing maybe a particular course, he does not share any modules with. So you can start looking at the relationships using the Venn diagrams. So those occurrences that happen are what we call the set operations. Okay? So we say set operations include set union. Now, set union is more or less an addition operation. There are different types of sets when we are using Venn diagrams. Okay? Set union, set intersection. Intersection is where you have a particular set of data having similar data with another. Okay? It means that some information that is in set A is also in set B. If, for example, I say students trying to get the number of students who are doing BIT and they're also doing computer science, you'll find that there are students in computer science who are doing maybe discrete math, and you're also having students in IT who are doing. So that number that is sharing that component is called the intersection. Okay? Then we have set difference. Okay? Set difference. Set difference, you are looking at those who belong in one oval, and you remove out those who are in another set, and they don't need to be, but we shall be able to see that. Then set complement as an operation would be what is not. How do I explain that? Complement. If I say that there are 500, there are 1,000 students doing in the universe of Faculty of Science and Technology, and then I say 200 students are doing information technology. Okay? Now, information technology complement is a group of students who are not at all doing information technology. So what number is that? 800. Okay? So when we say complement is we are saying not. If it's a complement, we are saying those who are not A. So all the rest become, or if I have A and B and I'm saying not A, it means all those who are A but not in B. Okay? So using that diagram there, who is the duster? Do you have a duster? Okay. So, but anyway, so we are now having an example of set A having 10, 11, 12, 13. Okay? 11, 12, 13. And then set B having 13, 14, 15. 13, 14, 15. Okay? Now we are talking about set union. Set. So set union is where we are adding. In set union, you are adding all the elements in A to elements in B. Okay? And we usually represent this by, can I have somebody that show a piece of paper? But we had our duster here. Who took it away? A piece of paper? So you will have your sets. Okay? Sometimes for you to represent union set, you will just have a U on that line to say this will be the universe. Okay? But now inside that universe, you have A, and then you have B. So you can put A there, put B there. Okay? Now in Venn diagrams, if you are trying to shape out A union B, it simply means get the whole of A, okay, and also the whole of B. So you're only shading part A and B. It means we want all the elements that are in A and B. Okay? Now, if you're making this representation, we shall say A union B. That's how they make the representation. A union B now consists of all the elements in A and B. Now, who can tell me the elements in A union B? 11, 12, 14, 13, 14, 15. Okay? Now, how many elements are here? And here? How many elements are here? So, how will you justify that you have 3 elements here, you have 3 elements here, but you have 5 here? Yeah? One is repeated. And because we said that we cannot be able, you don't go there and say because 13 is repeated. Remember we talked about an ordered list, okay? So you don't make a repetition, okay? We are going to look later at what we call, did we look at cardinality? Eh? What did we say cardinality was? The number of elements. So if I ask you the cardinality of A union B, it's actually going to be 5. Others will just be mixing. They are small things, but they become. So this is how A union B is going to look like. Okay. Now, maybe just at this point, let me still re-emphasize cardinality, because cardinality is usually very commonly asked question where there are operations. That after these operations, how many elements are? Okay. So we say cardinality over set. Cardinality over set. Are you for discrete math? Okay. Cardinality over set. Cardinality over set refers to the number of elements in a particular set. So cardinality of set A is 3. Now we usually represent cardinality by having it in, yeah. So if I showed you, I can ask you to say cardinality, or I can just ask you find that. What I mean is that tell me how many elements are in A, and that is 3. Then how many elements are in B? That is also 3. How many elements are in A union B? And I ask you that, that would be 5. Is that okay? Okay. Now, set intersection. Set intersection. Set intersection. Now, set intersection where you have A, it's represented by A intersection B. You have that down-sided cone. That shows intersection. Okay? So if I have A is equal to 11, 12, 13, and I have B is equal to 13, 14, 15, okay? And then I'm looking for A intersection B. I'm looking for A intersection B. What are we going to have? 13. Okay? Why? Yeah? Okay. So 13, because it's the one common between A and B. When you look at the elements here, you're looking for the element that is common between the two. Now, when you are using a Venn diagram, how does that appear? When you're using a Venn diagram, so you will have the universe, U, then you'll have A, then you'll have B. So for you to draw that, you need to draw the elements that are only in A, which are 11, 12, okay? Draw also only the elements that are in B, which are 14 and 15. And then draw the common element between the two, which is 13. Okay? But when I ask you, I saw very many students last semester. They will just draw things like this and leave it for you there. My friend, you're trying to show me which part represents the intersection. So you're supposed to come and shade that part, knowing that this is the only specific part we are interested at that material moment, the intersection. Are we together? When we talked about A intersection B, what did we do? We shaded the whole area. When we talked about the intersection, we have shaded only the part where A and B intersect. Okay? Then we have what we call set difference. Set difference. Set difference. Or relative difference. Set difference or relative. The set difference of sets A and B is usually denoted by A minus B. Okay? Is the set of elements which are only in A but not in B. Okay? So if A is equal to 10, 11, 12, and B is equal to 13, 14, 15. 13, 14, 15. Okay? So we can represent A minus B, and we have said A minus B is a set of elements which are only in A but not in B. So which elements are in A but not in B? Yeah? 10, 11, yeah? 12. Okay? 10, 11. So that would be A minus B. What about B minus A? 13, 14, 15. Really? 10, 11. No, no. A minus B. Why am I seeing something different? 14, 13, 14, 15. Oh, this was 10, 11, 12, 13. Sorry. A was 12, 11, 13. And B was 13, 14, 15. So A minus B was this. What is B minus A? 14, D. Okay? Whatever that I have, you don't have. So you click it out. If we share anything, you still cut it out. Okay? So, how do you represent this in a Venn diagram? How do you represent this in a Venn diagram? So, in a Venn diagram, A minus B will have that. Then you will have A, and then you will have B. So in A, we have 10, 11, 12, 13. Then in B, we have 14 and 15. So which part do you think A minus B? Which part do you think we shared? Yeah? A negative. There are those even who are not sure, but they're saying this side, this side. Yeah. So you will only share that part and leave the other side. So you're trying to you are here trying to if I said A minus B complement, what are you going to share? You're going to say? You're sure? Yeah? You shared the intersection and the other side of the man is saying, what are you talking about? Are you getting what they are saying? Or you don't believe? You can give us also an idea. Yeah? Now, is it only that part that you will shade? It means that this part is the only part you are not going to touch, but you will shade these whole things. Yeah? Yeah. You are saying complement, it means not A minus B. So you will shade the whole diagram. It means there are some elements you are not privy to here, but still they will be part, if they're in the universe, they will still be part of A minus complement. Okay. Complement over set. Complement over set. a set. So complement of a set, I've already told you, is so it is more or less what is not in that particular set. So we say the complement of set A, usually denoted by A, you can represent A complement. You put, what do we call this? An apostrophe. Yeah? Yeah. Or you can still represent this as that, sometimes. Okay? So this means A complement. So we are simply saying what is not A. Okay? So if I had the universe of a set U and I had A complement. Okay? So A complement would be what is not A, but is within that universe. Okay? If I said A union B complement, A union B complement, then that would be A, B in the universe U. So it would be whatever that is not A. Okay. Yeah, that's just a simple way of making the representation of those numbers. Now let's look at what we call Cartesian product. Cartesian. Sets. Product. Product, when we talk about product, you know it's majorly about multiplication. Yeah? So if we have set A, let's say we have set A is equal to A, B. We have set B is equal to 1, 2. Okay? We use Cartesian products to relate elements from one set to group actually elements.
Excuse me,
and try to
Ivan.
find out particular relations, to extract certain relations that exist between elements from one set to
Evans.
another. Okay. So what we mean here, you try to look at multiplying elements at that point, 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 and you try to create pairs. Actually, the best way to say is that when you are looking at the Cartesian product, you are actually looking at the pairing of the elements from different sets so that you can create and establish a relationship. Can you think about maybe we had, what would be a good example? You have pricing of items, then maybe the other one you have a different type of items. Mangoes, carrots, onions. But in the other set, you have the different price tags for those elements. 10 shillings, 5 shillings, 7. So when you create a Cartesian product, sometimes actually in mathematics, you can be able to connect elements at different levels and extract a formula to demonstrate the relationship. Okay? As we are going to see later what they call relations and things of that kind. So here you're just trying to pair. So if, for example, I have AB, A times that, if I start looking at A times B, okay? What we have said we are pairing. So you get the first pair. There will be, for you to represent them, you put them in brackets, each of the pairs. So the first pair here will be A will go with 1. You have that pair. Okay? So in the Cartesian project, you are extracting the pairs. So number 2, you will have A 2. Okay? Number 3, you will have B 1. And number 4, you will have B 2. Then you will close the braces. So one important thing is that in the Cartesian product, you are representing the pairs as elements. Are we together? You're not having the individual, but you are representing the pairs. Because remember, with the Cartesian product, you're looking at the relationship between the elements in set A and the elements in set B. Okay? If, for example, these are quantifiable numbers, you can even plot a graph and establish whether there is maybe a linear relationship between those elements or there is a non-linear relationship. You can do so many things. You can even draw a pie chart from these two. Okay? Yeah. So the question is A times B the same as B times A? Why will it not be the same and yet they are coming from the same sets? Eh? Speak loud. The order of arrangement. Because remember, like if I was saying, in set A I have mangoes, I have onions, I have pawpaws, and in set B I've put the price subsequently in that order. Whenever you change, you're not talking about the same thing. Okay? So when you have B times A here, instead you are going to have things now running the other way because it is 1A, then it is 1B, then it is 2A, and then 2B. Now this A times B is not the same as B times A. Yes.
I'm going to set is the elements in the set, the order is not an issue, so it is considered an order. Special partial order.
Come again.
Elements in the set they don't take a particular order. The set is unordered.
Unordered, yes.
So if the set is unordered, it means that A times B should be the same as B times A because the elements that are as a result of A times B will still appear the same. It's just that the order changes, but the order doesn't matter in sets.
Okay. Now that that is very perfect reasoning, but we are just saying what you're saying is very powerful critical thinking, because we are saying sets are unordered. But now we are going to find, as we go into relations, that in relations are ordered. But relations still come from sets. That when you are having a relationship, there must be certain order of sequence while it is coming from sets. Because remember that what we are doing, that as we are looking at set A and B, we're just trying to say that so long as I'm talking about sets, it doesn't matter the order. But whenever I'm picking, because set A is not the same as set B, do we agree? Set A is a different set. The rules that apply to that are completely different rules that apply to set B, especially when there is a relationship that exists between A and B. So you'll find later, while we're looking at Cartesian product, and as we're going to look at what we call relations, is that when you are studying elements in another set, in fact, another set B, and you are trying to establish a relationship, there is orderliness. You don't, it means that now here you have a little bit gone a notch higher, because you are looking at elements of one set being inferred to another set, so there must be a relationship. Okay, I'll give an example. Let's look at set A of different courses that are being offered in the Faculty of Science and Technology. Can we start naming the courses? Just a minute. So we have set A, courses that are being offered in the Faculty of Science and Technology. What would you have? BIT, BCS, DIT, okay, and on and on. Now what I'm saying, if I say that A is equal to DIT, BCS, BIT, this set is not different from that set. That's what I mean. Okay? Now, if I get another set B and say the number of students doing each of these courses, okay? Then I come and find how many students are doing DIT. Let's give a number, maybe 10. How many are doing BCS? Maybe 15. How many are doing DIT? Maybe 50. And I close. Now I have two sets. This set shows me the courses. This set here has been organized in relation to this in terms of the number of students. Now, if I am looking at the relationship, I will come back and say A
We have lost you, sir.
this number here dictates the number of students here. Okay? It's more or less like a command being inferred from BIT to go to numbers. But you can't interchange 10 to BIT. You understand? Because it is the course that is dictating the numbers, not the numbers dictating the. Are we together? So in other words, where there is a relationship, you have to consciously be able to analyze it, but you will see because after this topic we shall be looking at relations and functions. Yeah, trying to see where you have two sets, how you can be able to what a function is. We are going to define what a function is mathematically. Okay. Now, power set. Power set. Power set. Power set. Now we say power set over set S. Now, if we say how we represent that, we put P and S. That means power set. You have a set S, and then you are trying to get its power. So power set over set S is the set of all subsets of S, including an empty set. And the cardinality of power set of S is 2 to power n. Okay? So let's see. You have set S is equal to A, B, C, D. You have that A, B, C, D. So we're saying power set S is the set of all subsets of S, including empty set. So when we talk about, for example, we've been looking at cardinality. Yeah? So here you will take element
Hey guys, am I the only one not hearing?
I think we lost him. Yes.
okay. Livingstone, can you hear me?
Yes, yes, I can hear you.
I can't hear you, Livingstone. Is it my...
I can hear you, sir. Hello?
Kalanzi, can you hear me? Kalanzi.
Sir, we can hear you.
They are getting you right and clear.
We can hear you, sir.
I don't seem to get you guys. Okay.
We can hear you.
You are loud and
Please
clear.
type on the screen. I can't hear you. I just hope that... type in the screen if you can hear me.
Yes, we can hear you clearly, sir.
I mean, in the chat. Oh, okay, good. Okay, so now we're talking about power sets. We're talking about power sets. Where were we? So we are saying power set. That power set of a set S is the set of all subsets of S, including the empty set. The cardinality of a power set of S is 2. We found the cardinality by saying 2 to power n. Okay? So we're seeing an example of power set S having A, B, C, D. How do we calculate the subsets? Now remember that when we talk about power set, we're looking at all the
Am I the only one not hearing again?
more or less like trying to multiply, to categorize the different elements. Okay. So how can we start shaping that? We can start by the empty set. Empty set is just written like that, or you can write that as that. Okay, that also means the same thing, because we have said even an empty set is part of. Okay, then let's look at the sets with single elements. Sets with single elements. A, B, C, D. Okay?
Excuse me, sir.
Yes.
You just use the symbol of an empty set, or you make a set containing an empty set.
No, when you say a set containing an empty set, that is a singleton.
So now, in this case, you just use the symbol.
Yeah, use the symbol. Because what I'm saying, okay, if I'm getting what you're saying, you want to say, you represent that and you put a 0 inside. Is that what you're saying?
You put that symbol in braces.
No, once you put anything in symbol, that is a set of that. Yeah? Once you put anything, now let's give an example. You want to say S. You want to say that and then you put an S inside? Is that what you're saying?
Yeah.
No, that means that is a set of S. So there is an element. Even if you put a 0 inside the braces, that is an element of that set. So that is a subset there. So this just simply means that set is empty. Or you use that 0 and then you cross, meaning it's not even 0. Even 0 does not exist. So now in the next type of subsets, you look at single elements. Now remember that the one we have just been calculating about cardinality, we were looking at pairs of connected elements. Here we are looking at subsets of. It sometimes disturbs students once you tell them calculate power S, then they are showing you pairs of, or they don't know how this now gets different from. So you start with an empty set. You then go and represent individual elements. Then the next set, you start representing the pair subsets. Okay? So you will go and say this is AB, because AA is not, you don't have that repetition. So you will say you represent set A, B. Okay? Then you have set A, C. Then you have set A, B. Okay? Then B. Then you'll have B. Why is BA not there? Oh, no, I think BA is not there because this. Yeah, okay. So you'll have B, BC. Then you'll have BD. Again, remember the principle of the unorderedness. Now here applies. Because here we are not looking at, we are looking at the subset. We are not looking at the pair. Hey. Yes. Now, what we are saying, when you talk about a power of a set, you are trying to assess, from the definition, you're just looking at all subsets of that particular set. Okay? All subsets. So you are saying that depending on the number of elements you have in that set, you can still be able to break down all the possible small units that that set can have. And now we have defined and said that for you to get all the small units, it includes all the combinations of the small breakdowns, including even the one that is empty. So that's why we started that. We started by saying an empty set is still a subset of this set. Then we are going to get that which different combinations of single set can we have? We have A, we have B, we have C, we have D. Then because we have 4 elements, as we realize, we shall go from empty, go to 1, 1, go to 2, 2, go to 3, until we get to 4. Actually, it means that with this, you learn that you start from the empty set until you get to the maximum number of elements in that set as a combination. Okay? So here we are now shown. Now we go, if we went to the 3, we shall have a set of A, B, C, comma, then we shall go to A, B, D, comma, then we shall go to ACD, comma, then we shall go to BC, comma. Okay? Now that is for 3. Now lastly, we shall go to the one of 4 elements, which shall be A, B, C, and D. Okay? Yes. Come again? It's quite. And now you don't confuse. So by the way, if you are trying to look at the subsets, because the others you are going to try to combine them. But some of the obvious sets that you are going to subsets. First of all, this means that when you are looking at a subset of a set in a power set, there are 2 sets which are very obvious. Number 1, empty set. Number 2, the set itself. Are we together? So if, for example, I had X, Y, Z as a set, and I'm trying to look at the power set, the first set will be the empty set, and the obvious one again that will be there will be X, Y, Z. You understand? The rest, you can now start saying X, Y, X, Z. Maybe you understand what I mean? So, the set itself and the empty set are part of the power set. And that's why, for example, now here, the maximum set is going to have how many elements? Maximum subset, 3. So I'm going to have empty set. I'm going to have a set of X, a set of Y, set of Z as single set. Then I'm going to have a set of XY, XZ. You understand? Then I'm going to have a set of XY, Z. Okay? Remember, we are developing thinking systems. So, now when I talk about power set P, it shall be as follows. So power set P. No, power set S. So I will have a subset collection of set, empty set, okay? I will have A, I'll have B, I'll have C, I'll have D, I'll have A, B, I'll have A, C, I'll have C, there is no A, B. It's C. It's A, B. I'll have BC. And I'll have BD. Then I'll have CD. A, B, C. Then A, B, B. Then I'll have BCD. Then I'll have A, B, C, now let's say let it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now, how many elements? What is the cardinality of power S? Is 15, right? So there is one we have missed. So we usually say for you to find the cardinality of S, it is equal to 2 to power n, where n are the number of elements in that set. So one way of also guiding whatever you are calculating. So our 2 to power n should be 16. Are these elements 16? What have we left out? Yeah? They are 15. No, here. I'm trying to see what we have. Yeah? We have ABC. We have ABD. We have SCD. We didn't put SC. So that we have 16 elements. You have 16 elements. Do we have any question up to that point? Power of sets, cardinality of sets, Venn diagrams. Okay. Any question? Did somebody get the attendance list? Attendance list? Now, do you have groups? You have not set up groups.
Yes, we have them.
I don't know how you're going to set up groups. I want to. The online students, do you have groups?
Yes, we have groups, but I think it's for another different class.
They are
No, we don't have groups.
everywhere with different classes.
We don't have groups. We don't have groups.
I can't hear you guys. I don't know why.
The
We-
groups we have are for different classes.
Even if you have for different course units, you can still use it. Okay. It's because I wanted to give you. Yeah, but I think you can. Maybe I can give you a question and you still do on your own. You understand what I mean? The reason why we sometimes give a groups is for parts of discussion and for you to. But the questions I give you, take them very serious because you are most likely going to find them in your card. You understand what I mean? Yeah. So I'm going to give you a question. Paul, if you have a question, just type because I can't hear you. I don't know what the problem is with my laptop. You type it in the chat. I may give you a question. You go and research. How many of you did the previous assignment? Eh? You don't even remember. You did. So do you know whether you passed or have you discussed with your colleagues? I may not have time to look at that, but I hope you're all at par. Even those who have come and you've come today, please get those small assignments. It's a way of being sure, because sometimes the brain can lie to you that you understand. Not until when you have exam, then you realize. Because we had, I think the question was on using set builder notation to represent prime numbers between 1 and 10. Use set builder notation to represent numbers between 1 and 10. I'm just looking at the skill of your skill of being able to see how you can represent prime numbers, or how you can represent even numbers. Okay. 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 Yeah, so what I'm saying, you can use those groups, but the question I'm going to give you is just an application question. Go and use it to see whether you can, I'm going to get you one of the exam question that involved a number of sets, a number of elements in a set. Yeah, you try to create a diagram, you try to create the number of students and stuff like that. Okay, I'll put it on the WhatsApp group and I'll also put it on the chat. Okay, any question in this class here? Okay. Anyway, so that represents the end of our class. Let me post the question in the right away. The earlier you do these questions, the better. Don't make them pile. They will give you headache. They will give you headache. Discrete math. Okay, I've posted the work on Clannad. Do I need to put it in the WhatsApp group? All of you have Clannad accounts. Hey, you haven't paid our money. Eh? They have not yet opened. Ah, that is now you are changing. Okay. So, okay, let me put this in what? I put this in a Word document. Okay. Anyway, this marks the end of the class. I have posted the assignment on Clannad. but I'm also going to put the work on the WhatsApp group straight away. Those who have groups, this is for your personal health, okay? If you have groups and you can have discussions, the better, okay? Unless there's any other question, the online, I would love to leave you. Okay, bye-bye.